In this section, let's take a look at inverse trigonometric functions.
This is not a new definition. This is something you would have seen in algebra. Let's just remind ourselves again of what that is. Let f and g be functions. All right? If the composition of f of g of x is equal to just x for every value of x in the domain of g, and the composition g of f of x is also equal to x for every x in the domain of f, then f and g are called inverses of each other. You can say they're inverse functions, or you can just say they are inverses of each other. All right, what we mean by that is a function composed with another function. If these two functions give you back the original argument, then in a way they sort of undid each other and left you just the original argument, then they are inverses. They undo each other. Now, one of the first examples that you see of an inverse function is the square root function. So for example, we say we want f of x to be x squared, and we want g of x to be the square root of x, and here we take the positive root. Then, if you compose these, f of g of x, meaning g inside of f, meaning square root of x inside of x squared, is going to be square root of x quantity squared, which gives us just x. And likewise, if you have these the other way around, if you want g of f of x, then that's going to be x squared inside of that square root, which again gives us x. But you'll recall that this is not invertible the way it originally is drawn out, or the way it's originally written. Because one of the things that's true for a function is that if it is invertible, if you can find its inverse, that's true if and only if it's 1-to-1. So here I'm going to say recall that a function f is invertible if and only if f is 1-to-1. Being 1-to-1 essentially meaning every x value is paired with a unique y value, and every y value is paired with a unique x value. All right. But if you note, that means that this function shouldn't be invertible. Because after all, the graph of f of x equals x squared, that's a parabola, which starts at the origin and goes up in both directions. But that is not a 1-to-1 function. Because, okay, yeah, if I choose an x value, that does give me a unique y value. If I choose x is equal to 1, the y value has to be 1. If I say x is equal to 2, the y value has to be 4. So every x value does have a unique y value, but the opposite is not true. Look, if I choose this y value, I have two different x values. I have positive 1 and negative 1. If I choose y to equal to 1, positive 1 and negative 1 are both x values for that one y value. So here, this is not a 1-to-1 function. But if it's not 1-to-1, that means it should not be invertible. And yet, here we have it. The square root and the square are inverses of each other. So how do we justify that? Well, of course, you know the answer to that. We've seen that in algebra, and that is this function is not invertible. But a restriction of this function is. So here we say f of x is equal to x squared for x being greater than or equal to 0. Because once you say I want this function restricted to the positive values, here this is f of x equals to x squared. The entire function is not invertible. But a restriction of that function by saying, okay, let me just take the part from 0 to the right, that is 1 to 1. Every x value pairs with one y value, and every y value pairs with one x value. So here, with a restriction, f of x equals to x squared, given that x must be greater than or equal to 0, that is invertible. So note that even if a function is not 1 to 1, we can still talk about an inverse, at least for part of it, by restricting it to a portion that's 1 to 1. We're going to need that same concept to talk about the inverses of the trigonometric functions. Because remember that every trigonometric function is periodic. So here, let's take a graph of f of x equals the sine of x. We remember what that looks like going back to chapter 4. If this is x, and this is the sine of x, we recall that the sine of 0 is 0. It starts at 0. It goes up to a maximum of 1, and then down to a minimum of negative 1, and then finally comes back up to the axis. So the graph of f of x equals the sine of x looks something like this. And that's 0, and that's pi over 2, and that's pi, that's 3 pi over 2, and that's 2 pi. And of course, that does continue on forever, right? That is the central period of the sine of x, but this does keep on going. After all, I can draw the next period going to the right, and I could draw another period going to the left. And that keeps on going forever and ever and ever. So the graph of f of x equals sine of x is definitely not 1 to 1. Because notice, here, I have x equals pi over 2. Okay, that gives me y is equal to 1. Right, that would be the maximum up here. That would be 1. But notice that's not the only number that makes that happen. If I say x is equal to 7 pi over 2, that would also give me a y value of 1. And back here, if I say negative 3 pi over 2, well, that would also give me a y value of 1. So this is definitely not a 1 to 1 function. So note, periodic functions, and this isn't true of just sine, this is true of every periodic function, sort of by definition. Periodic functions are not 1 to 1. By definition. After all, by definition, a periodic function, that means that eventually you're going to have some other x value, which gives you the same y value. And not only is it going to happen again, it's going to happen indefinitely, forever, at regular intervals. So that means that sine of x is not invertible. So then I guess that's the shortest section of the course, right? Because we just say, oh, it's not invertible and we're done. Well, no. Because here, this was not invertible either until we restricted it. So here, this is not invertible. And there's nothing we can do about that. However, we can look at a related function. We can take a look at a restriction of this function. So let's say we have f of x is equal to the sine of x, but now we're going to restrict it. Okay, so where do we want to restrict it? Well, there's a few different choices we could make. Well, actually, I take that back. There's an infinite number of choices we can make. After all, we can take a piece of the graph from over here, from over here, from over here. There's lots of choices we can make. However, the traditional choice is the one that uses the smallest values of x. So in other words, one that touches 0. So we want some restriction that is going to include this x value. We want to include the smallest numbers possible. And we want to make sure that it's a 1-to-1 function. We want to make sure that we don't have multiple copies of the same x value or multiple copies of the same y value. Okay, well, this being a function, we can't have multiple copies of the same x value, but we have multiple copies of the same y value if we go out too far. So let's say we took from 0 to pi over 2. Oh, well, here we notice right here, this and this are the same y value. Okay, so that's too far. So if I restrict it just to right there. Oh, there we go. From 0 to pi over 2, there are no repetitions of any x value or any y value. I use all the numbers from 0 to 1 only once. And for my x values, I use the numbers from 0 to pi over 2 only once. The problem is that misses some points that we could have included. For example, here, this makes it look like the sign of x should always go between 0 and 1. And really, it should go down to -1. Oh, so if we include this part, that'll give us every possible y value we would normally have from -1 to 1, from -1 up to 1, but it only gives us each of those y values once. So here, the traditional choice, and again, there are other choices we could make. The traditional choice is to take f of x equals the sine of x and restrict it so that x is in the interval from -pi over 2 to +pi over 2. And that includes both of those endpoints, from -pi over 2 to +pi over 2. Okay? If we restrict ourselves that way, then we have a graph that looks like this. It's still going to go to a maximum of 1. It's still going to go to a minimum of -1. But now instead of moving along the x-axis forever in both directions, we're simply going to restrict ourselves to stay between +pi over 2 and -pi over 2. And that's just going to be this part here. It's going to cross through the origin, and it's going to look something like this. This is a portion of the sine function, but this portion is 1-to-1. Or at least it would be if I could draw a little better. There we go. All right, so that's an invertible function, or at least an invertible part of a much bigger function. So now let's define its inverse. Remember how that works? To define an inverse, that means you want the function whose composition gives you back the original argument, the original x. So what that means is the following, and I'm going to go to another page here. That means that if we have y is equal to the sine of x, what we want is some expression, some function, some operation that we could apply to both sides of this equation so that this x would now be left by itself. Basically, we want some way of undoing the fact that there's a sign here, sine of x. We just want x by itself. The way we do that is we take these and we reverse them. So if y equals the sine of x is the original function, then we can define an inverse function in the following way. And in fact, let's actually write that as a definition. So definition, the notation for the inverse of a trig function is written this way: sine inverse of x. Right? I'll go ahead and mention, there's a second notation for the inverse sign. It's called the arc sign. We mentioned that once before at the very beginning of our course, but back then we were talking about it strictly computationally. Back then we were talking about strictly as here's a button you're going to press on a calculator. Now we're going to talk about it a little more theoretically. I'm going to define it using this notation, but then at the end we'll come back and we'll remind ourselves of the other notation. So y equals sine inverse of x means that the sine of y is equal to x. Now, of course, this is restricted. We have to have that this result is going to be something you could take the sine of, which, given our restriction in the previous graph here, that means we want y to be restricted between -pi over 2 and pi over 2. For y in the interval from -pi over 2 to +pi over 2. Just like that. Okay, so first of all, a little bit about notation, and then we'll look at some examples. The first thing about notation is, what that means is, if I have y equals to the sine of x, What I want to do is I want to take the sine inverse of both sides. I want to use this operation. Sine inverse of the left side is equal to the sine inverse of the right side. Okay, so I began with the equation y equals sine of x, and now I'm going to apply this kind of operation to both sides. So the sine inverse of y is equal to the sine inverse of the sine of x. The notation, the way it's written here, suggests that these two should essentially go away. They should undo each other, and you should be left with just the argument x. All right? So that's the motivation behind this kind of notation, behind this kind of expression of sine inverse. It's the operation that you're going to use to get rid of the sine function. All right? Now, here, notice that this is defining it as y equals the sine of x. Here, we're defining y equals the inverse sine of x. So here, we're putting the focus on the sine inverse is the operation, whereas over here, we're putting the focus on the sine inverse was something that we used to get rid of the sine operation. Both of these are valid ways of thinking about them. They're either this is its own function, or it's an operation that I can use to get rid of an existing function. They're both correct, and they're both meaningful and useful in different contexts at different times. All right, so let's take a little closer look at this one here. We're going to take y equals the sine inverse, and here let's actually use a number. So let's say y is equal to the sine inverse of, let's say 1/2, just like that. Okay. By our definition, if y is equal to the sine inverse of 1/2, that means that the sine of y, so these are the same thing, the double-sided arrow means these are equivalent. One is true if the other one's true. If y equals the sine inverse of this, that means that the sine of y is equal to this. So if y equals sine inverse of 1/2, that means sine of y is equal to that x, which in our example is 1/2. Okay. Note, we know how to do that. You're going to take the sine of a number and you're going to get 1/2. You say, well, there's lots of numbers that do that though. There's lots of numbers that I can take the sine of to get 1/2. Well, yeah, but remember, we have a restriction. We have to find a number whose sine is 1/2, but that number has to rest between negative pi over 2 and pi over 2. So, for example, we know that sine of 5 pi over 6 is equal to 1/2, but that's not going to be a valid answer. Because here, by the restriction of our domain of the sine function that allows us to define the inverse function, that wouldn't fit inside of this restriction. Sine of 5 pi over 6 is 1/2, but 5 pi over 6 is not between negative pi over 2 and positive pi over 2. If you have a hard time seeing that, pi divided by 2, that's negative 1.7, negative 1.57. Which means this goes from negative 1.57 to positive 1.57, more or less. Okay, I know the sine of 5 pi over 6 is equal to 1/2, but notice 5 times pi divided by 6, that's 2.61. That's too big. That doesn't fall inside that interval between negative 1.57 and positive 1.57. So here, there's lots of numbers that make that true, but we want the one in here. Okay, well, the only number in between here that gives the sine value of 1/2, that's going to be pi over 6. Since the sine of pi over 6 is equal to 1/2, that means that this pi over 6 is that y, which means, by our definition, it's that y. So that means that the sine inverse of 1/2 is pi over 6. Essentially, if you ask for the sine inverse of a number, what you're asking for is, what number do I take the sine of to get that? If I want the sine inverse of 1/2, what do I take the sine of to get 1/2? Oh, well, you have more than one answer? Okay, pick the one that's in here, and that'll get you the correct answer. The same thing will be true of all of our other trig functions. So here, let's take a look at a quick sketch of the graphs along with the restrictions, and we'll define all of our inverse functions. Let's go back quickly to this illustration. F of x equals the sine of x. Thinking back to college algebra, one of the things that we learn about inverse functions, if you took algebra with us here in the previous semester, that would have been right around the middle of the second chapter. But wherever you took it or whatever you, however you saw it, we note that whenever you have a function and its inverse, the graphs are reflections of each other. For example, here, if this is f of x equals x squared, or at least that half of it, the inverse of x squared, for x being greater than or equal to 1, is the square root of x, the positive square root. Okay, this right here is the positive square root of x. Notice that these are reflections of each other, not across the x-axis. One would be up here and one would be down here. And they're not reflections across the y-axis. One would be over here and one would be over here on the left. Rather, they're reflections of each other across this line, which is the line x equals to y. That's true of any function and its inverse. If you graph a function and its inverse, they are reflections of each other across the line x equals to y. And since we are defining an inverse of the sine function, the same thing must be true here. So here, this would be a reflection across the functions, across the line x equals to y. So here, the graph looks something like this. This reflection would come down across the origin and then down across like this. Unfortunately, my graph here is not to scale. It does give you the shape of the graph, but it doesn't exactly give you the scale. It doesn't tell you exactly what these points are. So here, I'm going to, in the next page, give you the more detailed graphs of those. So here we get the idea as to, okay, that's what the shape is. It's going to look something like this. It's going to be a reflection of this line across x equals to y. But now let's give the graphs with some more precise detail, along with the other definitions of the inverse trig functions. All right, so let's give I guess we'll give the definitions here alongside the graphs. So let's see here. These are all definitions. And I may as well repeat this one to keep them all together. The sine inverse of x, that's the same as saying that the sine of y is equal to x for x in the interval from, for y in the interval from minus pi over 2 to pi over 2. Okay? There is a symbol that this book will sometimes use whenever we're talking about intervals. If you want a variable to be in an interval, you can say y is in the interval, or you can say just y in, or you can use this symbol. This is a symbol from set notation. It kind of looks like the letter E. It means element. Y is an element of this set of numbers. It's just another way of saying y is somewhere in here. Y is one of the numbers that's in this interval. So here it kind of looks like the letter E. You make it by making like a C with a little line in the middle. So that's read as y as an element of this interval. Y is equal to the cosine inverse of x. And at this point, it takes no imagination to realize how we're going to define that. That's going to be the cosine of y is equal to x. For this one, we're going to have a restriction. For the sine function, we saw that the restriction that we wanted was the interval from negative pi over 2 to pi over 2. For the cosine function, it'll be a little bit different. I'm going to put that over here. For the cosine function, our graph starts at a maximum, comes down to a minimum, and then starts to come back up. Notice here, if we take the interval from 0 to right here, halfway between the central period, that already covers everything from the maximum down to the minimum. So here, our restriction will be a little different. It's still going to be the same length, but instead of starting in the negative and ending in the positive, here it's going to start at 0 and end at pi. So here we're going to want our restriction, we want our y to be an element of the interval from 0 to pi. Just like that. Y is equal to the tangent inverse of x. That's equivalent to saying that the tangent of y is equal to x. Now the tangent has its own natural restriction, because remember, the tangent of x has a graph where from negative pi over 2 to positive pi over 2, you have the central period, and at those two values, you have an asymptote. Within the interval between negative pi over 2 and pi over 2, this function is already one-to-one. So yeah, we could restrict it a different way, but this seems to work pretty well. It crosses through 0, and we have a one-to-one function within the central period. So the tangent, we're going to define the inverse tangent using values that are between the two intervals. Notice that's going to be the same as the definition of the restriction for the sine inverse. Or I said that backwards. It's going to be the same inverse as for the definition of the sine inverse, except this won't include the endpoints. Because of course, in the tangent function, the endpoints are not included. They would be asymptotes. So here we are going to say for y, in element of the interval from negative pi over 2 to positive pi over 2, but in this case it's an open interval. We don't include either endpoint. Now let's take a look at the reciprocal functions. The sine inverse, the reciprocal of the sine is what? The cosecant. So let's define the cosecant inverse of x, and that's given by whatever value of y we can take the cosecant of to get x. In other words, it continues to use the same definition as we have up here. So cosecant of y is equal to x. 4, and here we're going to go ahead and restrict ourselves between negative pi over 2 and positive pi over 2. Which makes sense, since you have this as the reciprocal of this, it makes sense that if this function is one-to-one, then this function will be one-to-one in the same interval. There is, however, one exception. You'll recall that the cosecant function has an asymptote right in the middle. Thinking back to chapter 4, when we graph the sine and the cosecant functions, if this was our sine function here, then wherever you have sine of x equals to 0, which is at 0 and at pi and at negative pi, here you have asymptotes. So if you're defining your inverse, if you're defining your reciprocal, if you're defining the cosecant's inverse, you want to still keep this portion from negative pi over 2 to positive pi over 2, but remember, at 0, it's undefined. So we're going to have the same restriction as we have when we define the inverse sine function, except we're going to exclude the point at 0. So here that's going to be y is an element of the interval from negative pi over 2 up to 0, and that does not include the 0, union with everything from 0 to pi over 2, like this. So it's the same as that one, except you're excluding the asymptote at 0. And the same thing will be true for the inverse secant. We're going to be using the same restriction as we used to define the inverse cosine, except again, we're going to want to exclude the asymptote that you would normally find when you define the secant function. So here we're going to take y equals the secant inverse of x, and that's going to be given by the secant of y equals to x for that same interval, excluding the asymptote, which, if you remember back to chapter 4, was going to be found at pi over 2. So this is going to be y is an element of the interval from 0 to pi over 2, union with the interval from pi over 2 up to pi. Same interval with a hole at pi over 2. And the cosecant, the cotangent, just like the tangent, is going to have unnaturally defined interval. The cotangent has a one-to-one portion already locked between the asymptotes. So we're going to take the interval between 0 and pi, which is just two consecutive asymptotes of the cotangent function. So y equals the cotangent inverse of x, and that just means that the cotangent of y is equal to x for y that is in the interval from 0 to pi. Oh, but since there are asymptotes at the endpoint, we would not include those endpoints as part of the interval. So that should be an open interval, not closed. It's just like the tangent. The endpoints have to be excluded because you have asymptotes there. The graphs of these functions note here we have that the range of your sine function, of your inverse sine function, the y values, are between negative pi over 2 and positive pi over 2. So down here, negative pi over 2, and up here, positive pi over 2. Our range, that should be, oh no, that's right, that's our y values. So now our domain should be the range of the sine function. After all, the x value are the numbers that you can get by plugging y into the sine function. Well, when you plug something into a sine function, you're going to get something between minus 1 and 1. So x has to be between minus 1 and 1. And our graph looks something like this. It's going to start up here at 1 comma pi over 2. It's going to cross to the origin and then come down here to negative 1 comma negative pi over 2. And it'll look like that, which you'll recognize as being a much nicer, a little bit smoother version of what I had before. This kind of shape right here. Starts off very steep, flattens out, and then ends up steep again. The inverse cosine will also have a graph. Here the y value is between 0 and pi, so it's going to start here at 0. It's going to go up to pi. And again, x is whatever values are coming out of the cosine function, which means x has to be between minus 1 and 1. So here, minus 1 and 1. And that's going to start up here at negative 1 comma pi. And then it's going to come down here to 1 comma 0. And then at 0 comma pi over 2, it's going to cross right here at the y-axis. So this will be pi over 2, halfway in between 0 and pi. And that'll look like this. Okay. The inverse tangent. Note that our y values from negative pi over 2 to positive pi over 2. And note that it does not include either of those because we're going to have asymptotes there. Just like the tangent has no restriction on what its result can be. In other words, I can take the tangent of something and get any number. Well, then that means that this x can be any number. So even though my y values are restricted between negative pi over 2 and positive pi over 2, my x values have no such restrictions. They go forever to the left and to the right, but again, you do have to follow your asymptotes. You can't pass through the asymptotes. Just like that. Incidentally, for those of you who are going on to pass trigonometry into calculus, this is a function that appears very often, largely because it is infinite in domain, but still has some nice boundaries to it. This is an example that's used a lot in some calculus problems, partially because it is not a especially simple function, but it is simple enough in certain respects. You'll see the inverse tangent function used fairly often in calculus courses. The cosecant function, the y value is going to go from negative pi over 2 up to a positive pi over 2. Like that. Note that we are going to be excluding 0. So it is going to have an asymptote there. Okay. And the graph of that looks like this. It's going to start, this is going to be the value 1, comma, pi over 2. It's going to come down and follow the asymptote. And then on this side, this is going to be the value -1. And it's going to start at -1, comma, negative pi over 2, and then follow the asymptote, just like that. Note that if you look back at our graph of the cosecant function and the secant function, they look something like this. If you imagine cutting that out so that you have the 1-to-1 portion, and then taking that and flipping it on its side, taking the 1-to-1 portion and flipping that on its side, you end up with well, that kind of a curve, and then separately that kind of a curve separated by an asymptote. That's what we have here. That kind of a curve and that kind of a curve separated by an asymptote. The secant function is going to look pretty much the same way, except the asymptote is going to be shifted over a bit. So note that this one starts at 0 and goes up to pi. But then you have your asymptote at pi over 2, your y value, pi over 2. And this is going to be 1, and this is going to be -1. And you're going to start at 1, comma 0. You're going to go up and follow your asymptote. And over here, you're going to start at -1, comma pi. And then you're going to go down and again following your asymptote. Just like that. And finally, cotangent is essentially going to be just a flipping of the tangent function, or rather the inverse tangent function. So here, this is going to be, it's going to have its asymptote at 0 and at pi. So here's 0 and up here's pi. And halfway in between, it's going to cross the y-axis, that pi over 2. And it's going to follow the asymptote, the upper asymptote on the left and the lower asymptote on the right. Here the x-axis does behave like an asymptote. And here are the graphs of our inverse trig functions. Notice we don't go through and spend a lot of time actually creating these point by point, mostly because they're not created point by point. They're created by using this concept. You already spent a lot of time in chapter 4 graphing the full details of a trig function. Reflecting that across the line x equals to y, as we learn in algebra, is sufficient to give us a sophisticated enough graph of the inverse function. And so here we do exactly that. Note that these are our ranges. This is the range of the inverse function. Remember, there is a domain, and here it's already stated in the graph, but let's go ahead and actually state that here. Note that that means that x has to be between -1 and 1 for this one. For this one, it's also between -1 and 1. For this one, it goes on forever in both directions. So x is an element of the real numbers from -infinity to infinity. Here, it is from 1 to infinity. And on this side, it's -infinity to -1. So here, x is an element of -infinity up to -1, union with 1 to infinity. Just like that. Same thing for this one. Exactly the same way. And finally, this one goes on forever to the left and to the right. So here x is bound between -infinity and infinity. It's a little strange to say it's bound by infinity, but all that means is that there's no boundary. Note that if you remember the graphs of all of these functions back in chapter 4, these are basically just flipped around. Right? Normally we have x would have these values, and y would be bound between -1 and 1. Right? Looking at the sine function, usually our x value is in terms of pi's, and our y value is between -1 and 1. Well, now it's backwards. Now the y value is in terms of multiples of pi, and the x value is between -1 and 1. And if you look back at all the graphs and the domains and ranges of the original trig function, sine, cosine, tangent, secant, cosecant, and cotangent, you'll notice the exact same pattern. For example, here, the range of the tangent function is from negative infinity to infinity. But here, the domain of the inverse tangent function is from negative infinity to infinity. Here, this would be the place along the x-axis where you have your asymptotes. Now, it's the place along the y-axis where you have your asymptotes. Right? Everything's flipped. All right, now, one of the key features of an inverse function, or rather, the key feature of two functions that are inverses of each other, is that they undo each other. Well, yes, but people often overlook the following restriction. Here, f of g of x is equal to x, and g of f of x is equal to x, but that only assumes that, that's only true if we assume that this x value is in the domain of g, and that then g of x is in the domain of f. In other words, yeah, okay, if you can plug that in there, and then that can be plugged into f, well then sure, these cancel out. But what if you couldn't? What if x is not in the domain of g? And what if g of x is not in the domain of f? Well, then maybe they don't quite cancel out. That's something that people take for granted with algebraic functions, things like x, x squared, and so forth, because it doesn't really come into effect there. It doesn't really cause us any issues, because the algebraic functions that we see either have an infinite domain, so from negative infinity to infinity, so there is no restriction. There is no time when that doesn't give you just x. Or in the worst case scenario, you might have something where you're restricted to just half the graph, where, okay, maybe these two don't cancel each other out perfectly, but the only difference is, oh, I'm sorry, it should be a negative versus a positive. Trig functions, however, are severely more restricted than that. Here you're looking at just a little tiny piece of an otherwise infinitely long domain. So what that means is when you take an inverse and compose it with its original function, yes, they should undo each other, but there are some cases where it doesn't quite work the way you expect it to. So let's take a look at some examples of how to compute something like that. Okay, so in fact, let's do several examples here of just using an inverse trig function. So let's begin with just a quick computation, just to remind ourselves of how these work. Let's say we want to find the cosine inverse of, let's say the square root of 3 over 2. Okay. All right, well, if I want to find the inverse cosine of root 3 over 2, that's going to equal to some number. Okay, great. So what? Well, what that means is I want the number where if I take the cosine of that number, it's going to give me that x value. It's going to give me root 3 over 2. But remember, that y value can't just be any y value. It has to be the y value between 0 and pi. It has to be the y value between 0 and pi. Okay, so I have lots of numbers whose cosine is root 3 over 2. In fact, I can think about the unit circle. If I want the cosine to be root 3 over 2, I could have that number there, or I could do this number down here. And that would be what? Pi over 6. And this would be 11 pi over 6. Both of those have a cosine of root 3 over 2. In fact, I could even go backwards. I could say, instead of saying that's a positive 11 pi over 6, I could say that's negative 1 pi over 6. All of these have a cosine of root 3 over 2. But again, we want the one that's between 0 and pi. On the graph, that would be, on the unit circle, that would be whichever one appears up here. From 0 to pi. Oh, so it's got to be that one. So here, cosine of pi over 6 is equal to root 3 over 2. That's the only one between 0 and pi. So what that means is that over here, the cosine inverse of root 3 over 2 has to equal to pi over 6. like that. All right, now let's take a look at another example where we're going to compose one function with another. Let's say I want to take the, let's do cosine inverse of the cosine of pi over 4. I'm also going to do another one. I'm going to do the cosine inverse of the cosine of, let's do 5 pi over 4. Okay. By our definition, if these two are inverses, composing them should just make everything go away, and I should just be left with that number. Same thing over here. If these are inverses, which I claim they are, I should be able to have these just go away, and I should just be left with an answer of 5 pi over 4. Well, that doesn't quite work that way. Because again, that would work that way if 5 pi over 4 was in the domain of the cosine of 5 pi over 4. If 5 pi over 4 was in the domain of the cosine, and then this was in the domain of the inverse cosine, and then this was in the range of the inverse cosine. And same thing over here. That's only going to be true. These are only going to cancel out if pi over 4 is in the domain of the cosine, and then if the cosine of pi over 4 is in the domain of the inverse cosine, and then if pi over 4 is in the range of the inverse cosine. If that's a little hard to follow, going through the example will highlight exactly what that means. So let's go through this. I'm going to just do this one step at a time. Forget about what should happen. Let's see what does happen. Cosine of pi over 4. Oh, well, that's just the square root of 2 over 2. So if I want the cosine inverse of the cosine of pi over 4, that's going to stay the same for this first step. But here, that's root 2 over 2. Well, now, what is this saying? Well, it's saying the cosine inverse of root 2 over 2, that's equal to some number. By our definition, that's the same as saying that the cosine of that y is equal to root 2 over 2. So again, we want to make sure that y is in the interval from 0 to pi, since we're still talking about an inverse cosine. If it was inverse sine, you'd have a different interval. All right, so we still want some number whose cosine is root 2 over 2. And again, we know a bunch of those. All right, we have pi over 4. We have 7 pi over 4. We have negative pi over 4, and so forth. There's lots of those. But there's only going to be one between 0 and pi. The only number between 0 and pi whose cosine is equal to root 2 over 2 is going to be pi over 4. All right? So here, that means that y is equal to pi over 4. So that means that in the end, that's my answer. I have that the cosine inverse of the cosine of pi over 4 is equal to pi over 4. So in this case, yeah, that's exactly what happened. The cosine inverse of the cosine sort of just went away, and I just left with pi over 4. Okay? But now look at the other example. Again, forget about what should happen. Let's see what does happen. What's the cosine of 5 pi over 4? All right, well, the cosine of 5 pi over 4, 5 pi over 4 is negative root 2 over 2. Okay, no problem. All right, I can take the cosine of 5 pi over 4. That's negative root 2 over 2. Now I want to take the inverse cosine. All right, well, remember, by our definition, what that means is that cosine inverse of negative root 2 over 2 is equal to y. That's equivalent. That's the exact same thing as saying that the cosine of y is equal to negative root 2 over 2. And you say, well, yeah, that's 5 pi over 4. After all, the cosine of 5 pi over 4 is negative root 2 over 2. But 5 pi over 4 is not between 0 and pi. We need a number that's up here in either quadrant 1 or quadrant 2. The only number in between 0 and pi whose cosine is negative root 2 over 2, that's 3 pi over 4. Yeah, 5 pi over 4, if I take the cosine of 5 pi over 4, I do get negative root 2 over 2. But that's not in the interval that I allow, right? That's not in the interval that I'm allowed. The interval that I'm allowed is everything from 0 to pi, which means 5 pi over 4 is not valid. 3 pi over 4, on the other hand, is valid. The cosine of 3 pi over 4 is negative root 2 over 2. So that suggests that y is equal to 3 pi over 4. Oh, okay. So then that means that the cosine inverse of the cosine of 5 pi over 4 is equal to 3 pi over 4. Notice how those didn't just go away. These are different. So now, let me repeat my statement from earlier, and hopefully it'll make a little more sense. Do these cancel out? Well, let's see. Is pi over 4 in the domain of the cosine? Sure, because I know how to take the cosine of pi over 4. Okay, cool, no problem. Okay, now I got an answer. Is that answer in the domain of the inverse cosine? Absolutely it is, because I know how to take the inverse cosine of that number. Okay, but now, the inverse cosine, okay, that's in the domain of the inverse cosine. It's something I could plug into the inverse cosine. But what about the range of the inverse cosine? What kind of answers can I get from the inverse cosine? Oh, well, the kind of answers I can get are from 0 to pi. Oh, is that number between 0 and pi? Is that in the range of my inverse cosine? Yeah, it is. Pi over 4 is between 0 and pi. Okay. So since this is in the domain of this whole thing is in the domain of this, and this original argument is in the range of the inverse cosine, then yeah, these two just canceled out and I got pi over 4. On the other hand, is 5 pi over 4 in the domain of the cosine? Absolutely. Okay, and that gives me negative root 2 over 2. Is that in the domain of the inverse cosine? Absolutely it is. I know how to take the inverse cosine of that number. Okay, but now, is this original argument in the range of the inverse cosine? Well, no. The range of the inverse cosine is between 0 and pi. 5 pi over 4 is too big. Oh, okay, so in that case, they won't just cancel out. That doesn't mean I can't get an answer, because clearly I got an answer, but it doesn't mean they can just cancel out. So be very mindful of that. Whenever you have a composition of a trig function and its inverse, if this number here is in the range of this inverse function, then sure, they'll just cancel out. But if this number here is not in the range of my inverse function, then no, they don't just cancel out. That doesn't mean I can't get an answer. It just means it may not be that answer. So here, give this a try. See if you can do that. Let's do the sine inverse. So the sine inverse of the sine of negative pi over 3. Okay. Just to remind you, y is in the interval from minus pi over 2 to pi over 2. Whenever you're dealing with a sine inverse, the range of the sine inverse is, here, let me write out the full definition here. Sine inverse of x equals to y is exactly the same as saying x is equal to the sine of y, so long as y is in that interval from minus pi over 2 to positive pi over 2. So give that a try. See if you can go through the whole concept of domain and range the way I did up here. That's great. Same thing over here. Or if not, then just take it one step at a time, and either way, you'll get a nice answer. Well, you'll get an answer anyway. So go ahead and give that one a try, and go ahead and give this one a try as well. Let's take the sine inverse of the sine of, let's say 3 pi over 4. All right. Go ahead and give both of those a try, and pause the video now. And once you get an answer, go ahead and unpause, and we'll finish it off together. All right, so here, all right, negative pi over 3 is definitely in the domain of the sine function. I can take the sine of that number, no problem. Okay, well, what is it? Well, let me not worry about that. Let me just check to see what's happening first. Is this in the domain of the sine function? Absolutely. Okay, so if I take that and I take its sign, it's somewhere between -1 and 1. Well, that's fine, because I know how to take the inverse sign of numbers between -1 and 1. Okay, so here nothing is outside of the domain of any function. This is in the domain of sine, and then that result is in the domain of the inverse sign. But now let's check this right here. Is this number in the range of the inverse sign? Is this some answer I could get by taking an inverse sign of something? Well, let's see. The inverse sign has a range from -pi/2 to pi/2. And sure enough, -pi/3 is in between those two numbers. If you're not sure about that, you can always grab a calculator and see what these are as decimals, and it makes it a little clearer that that is definitely in between those. Either way, that's in the domain of the sign, and that result is in the domain of the inverse sign, and this original argument is in the range of the inverse sign, so that is one of these examples where, yeah, these are just going to cancel out. And in the end, I'm going to get -pi/3. If you didn't want to go through it that way, you can always just compute it. You can say, okay, take the sine of -pi/3, and that's going to be -√3/2. And then I could take the inverse sine of -√3/2, and that's going to turn out to be -pi/3. So either way, you get that answer. This one, on the other hand, you'll note that it won't just cancel out. Because notice, yeah, okay, I can take the sine of that number, and that'll give me something between -1 and 1. And yeah, I can take the sine inverse of a number between -1 and 1. So no problems. All of these are in the correct domains. Right? But is 3pi/4 in the range of the inverse sign? Can I take the inverse sign of something and end up with 3pi/4? Well, clearly not. 3pi/4 is a lot bigger than pi/2. Well, a lot is sort of a general statement, right? It's sort of a arbitrary statement. What do we mean by a lot? Well, okay, let me just say it this way. It's greater than pi/2. Doesn't matter by how much. So here, these won't just cancel out. So here I actually have to go through and compute it. I won't just be able to say, oh, those just go away. All right, so the sine of 3pi/4, that's going to be √2/2. And now I want the sine inverse of √2/2. Let me draw out my circle here, because I know I have a few different numbers whose sine is √2/2. I know one of them right here is pi/4. And then over here there's another one that's 3pi/4. And I go all the way around, and that would be what? 9pi/4. And if I keep going, that would be 11pi/4, and so forth and so on. This is a periodic function. Of course, I have a lot of different values for that. But I don't want just any value. I want a value that's between -pi/2 and +pi/2. In other words, I want something from, here's -pi/2, here's +pi/2. The only number that I have that is between here and here is pi/4. You say, well, 9pi/4 is there too. Well, yeah, visually, it is coterminal to this angle, but note that 9pi/4 is significantly bigger than pi/2. Here, pi/4 is the only number that is not only in the right region, but it's also here in the correct interval. So here, that's going to be sine inverse of √2/2. That's equal to pi/4. So notice here, these don't just cancel out. The sine inverse of the sine of 3pi/4 is just pi/4. So be mindful of that. Whenever you see these paired together, yeah, they're going to simplify, but they won't always give you exactly the same number. If this is in the range of the inverse function, then yeah. If not, well, then it'll get you something different. Note that here and here, we compose a function and its inverse, cosine and inverse cosine, sine and inverse sine. It doesn't have to be just those pairings. What happens if I want to compose cosine with inverse sine? Well, here they have no hope of just canceling out. Here, these are inverse functions, and again, we do have some issues where they might not cancel out perfectly depending on the range of this outer function, but at least there's a chance. In some cases, they do cancel out perfectly, giving you just the original argument. But cosine and inverse sine are not inverses of each other at all in any way. So there's no chance of this one canceling this one. but they're still functions, which means I should still be able to compose them somehow. All right? Square and square root cancel out. Square and cube root do not cancel out. But I can still take the cube root of x squared. So how do I do that here? How do I take the composition of a function with the inverse of a different function? So let's go ahead and give some examples. The first one we're going to do is entirely numerical. It uses just numbers in the arguments of the original function. And then the next example we'll see involves a variable. And they work with the same technique, although it might look just a little different with the variable. All right, let's take the sine of the inverse cosine of a quarter. Okay, these have no hope of canceling out. There's no way it's going to be a quarter. Okay, so how do you do it? Well, let's start off with looking at just the cosine inverse of a quarter. Forget about the sine. We'll get to that later. You say, okay, so what? We're going to have to compute cosine inverse of a quarter? That sounds hard. Well, no, we're not going to compute it, at least not directly. What we're going to do is we're going to represent it a different way. The cosine inverse of a quarter is an angle. It's a what now? Well, it's an angle. If I say I have the cosine inverse of a quarter, that's equal to something, right? That is the inverse cosine of a quarter. Okay, but by our definition, that means that the cosine of y is equal to a quarter. Well, what do you take the cosine of? You take the cosine of an angle. That's what y is. When I take the inverse cosine of a number, I'm going to get an angle. And I can represent it as a set of radians. I can say, oh, okay, pi over 4, pi over 3, pi over 2. Or I could do it as the degree, 5 degrees, 10 degrees, 20 degrees. But whatever I represent it as, this is an angle. And if that's an angle, that's an angle. Okay, so what? It's an angle. Well, I have visual ways of representing angles. One way of doing that is with a right triangle. The cosine of y is equal to 1/4. Okay, well, here's your y. Let me put it inside of a right triangle, because that's one way of visually representing an angle. Here, it might get a little confusing if we use y, because sometimes we're going to want to use y for other purposes. You know, y equals something. So here, I'm going to go ahead and use the more traditional symbol for an angle. I'm going to say theta. Here, I'm not changing what any of this means. I'm just going to use a different symbol, mostly because it is sometimes a little confusing to use y in this context. So I'm going to just say theta instead of y. If you prefer, you can leave it as y. All right, so here, cosine of theta is equal to 1/4. Well, remember, one version of the definition of the cosine of theta is if theta is an angle situated in a right triangle, the cosine of theta is the side opposite divided by the length of the hypotenuse. Oh, I'm sorry, that should be adjacent over hypotenuse. The cosine of the angle theta is the length of the side adjacent over the length of the hypotenuse. Well, this is the side adjacent, so that's length 1. And this is the hypotenuse, so that's length 4. Okay? By the Pythagorean theorem, I can now fill in the rest of this triangle. I can now say, okay, well, look, 1 squared, let me call this side b, that's the one I don't know, right? A, b, and c. A squared plus b squared is equal to c squared. All right, 1 squared plus b squared is equal to 4 squared. That's 1 plus b squared is equal to 16. And if I subtract 1 from both sides, that gives me b squared is equal to 15. I can now take the square root of both sides. And that's going to give me plus or minus the square root of 15. But of course, that's the length of a side of a triangle. It can't be negative. So it must be positive. Okay, great. We've represented that angle theta in a triangle. So what? Well, look over here. Cosine inverse of 1/4, it is that angle. Yeah, so when I say I want to find the sine of cosine inverse of a quarter, what I mean is I want to find the sine of that angle theta. So sine of cosine inverse of a quarter, that's sine of theta. But I know how to find the sine of theta. Assuming that theta is an angle situated in a right triangle, the sine of theta is the side opposite divided by the side length of the hypotenuse. Well, the side opposite is root 15 in length, and the hypotenuse is 4. So here, the sine of theta is equal to root 15 opposite over 4. And that's our answer. The sine of the inverse cosine of a quarter is root 15 over 4. Go ahead and try that. Let's say we want to find the, and here we're going to say find the exact value. And remember, all that means is it wouldn't be anything that came out of a calculator. It would have to be an exact solution with a radical or with a fraction. A decimal is an approximation, and that's not going to be good enough. Here, we want to find the exact value of, let's say we want the cosine of the inverse tangent of, let's say, 3/5. All right. Go ahead and give that a try. Go through, and you can build it exactly the same way we did here. You can visually represent this, which is going to be an angle, and then find the cosine of that angle. Once you have a result, you can unpause the video, and we'll finish this one together. All right, so let's take a look. Here, I want to ignore the cosine for just a second. Let's take a look at just the argument, and that's the tan inverse of 3 over 5. And that's going to equal to an angle. Whenever you take the inverse something, inverse sine, cosine, tangent, secant, cosecant, cotangent, whenever you take an inverse trig function of a number, that result is going to be an angle. Okay, so inverse tangent of 3/5 is an angle. Well, which angle? Well, it's the angle that if you take the tangent of it, you're going to get 3 over 5. Okay, well, I know how to represent the tangent of an angle. I can draw it as a right triangle. Here, I'm going to take the angle theta. I'm going to situate it in a right triangle, not the 90-degree angle, one of the other two. And now the tangent of theta is going to be given by the side opposite divided by the side adjacent. All right, well, that means the side opposite's got a length of 3, and the side adjacent's got a length of 5. And so by the Pythagorean theorem, a squared plus b squared has to equal to c squared. Here are your a and b. So I'm going to say 5 squared plus 3 squared is equal to c squared. So 25 plus 9 is equal to c squared. Adding these together gives you 34 is equal to c squared. And finally, I could take the square root of both sides, and I get c is equal to plus or minus the square root of 34. But of course, the length of a hypotenuse cannot be a negative number, so it's got to be the positive. So that's going to be root 34, just like that. So that angle theta is the inverse tangent of 3/5. So when I say I want the cosine of the inverse tangent of 3/5, that means that I want the cosine of that angle. Oh, but the cosine of the angle theta, that's going to be the length of the side adjacent to theta divided by the length of the hypotenuse. That's going to be 5 root 34. 5 over root 34. And then, of course, we rationalize all of our numbers. So here we're going to multiply top and bottom by root 34. Multiply top and bottom by root 34. And so that's going to give us that the cosine of the angle theta, or here I'll write out the full problem, the cosine of the inverse tangent of 3 over 5, that's going to equal to 5 root 34 as my numerator. And in my denominator, root 34 times root 34, that's just the number 34. And that's our result. 5 root 34 over 34. Finally, as our last example, let's do one very much the same way, except now instead of having these both be numbers, both be constant numbers, let's have a variable or so. So let's go ahead and take the sine of the inverse cosine of x. Okay. Now, here, same as before, we're going to do the same thing. We're going to take this and treat it on its own. So we're going to say the cosine inverse of x is equal to an angle. That's what it means to take the inverse cosine of something. It means you're looking for the angle whose cosine is that expression. But by the definition of the inverse cosine, that's really saying that x is equal to the cosine of the angle theta. Right? If cosine inverse of x is equal to theta, by definition, the cosine of theta must equal to x. Now, this looks a little different than the previous ones because, after all, these were all fractions. Well, yeah, cosine is the length of the side adjacent to theta divided by the hypotenuse of a right triangle. Here, there's no fraction. You don't have, something over something. Well, sure you do. It's over 1. Anytime you have something that's just by itself, like the number 5 or the variable x, you can always think of it as being over 1. Oh, okay. So we can draw a right triangle to represent the value of that angle, theta. Theta is the angle situated in a right triangle whose cosine is x over 1. Okay, well, cosine of theta, that's the side adjacent, so that's going to be an x. The hypotenuse, well, that's the number 1. Right. Cosine of theta, that's the length of the side adjacent as the numerator. The length of the hypotenuse is the denominator. And now by the Pythagorean theorem, I have a squared plus b squared is equal to c squared. I know my a, that's just the variable x. I don't know b, so I'm going to leave it as b for now. But I know c is just the number 1. So this will give me x squared plus b squared is equal to 1. I can subtract x squared over to the other side, giving me b squared is 1 minus x squared. And I'll take the square root of both sides. I get b is equal to either plus or minus the square root of 1 minus x squared. But again, b is the length of the side of a triangle, so it can't be negative. So it's got to be the positive square root of 1 minus x squared. What is x? Well, we don't know. But whatever it is, this length will be 1 minus x squared inside of a square root. So when we say we want the sine of the inverse cosine of x, that means we want the sine of that angle theta. After all, that angle theta is the inverse cosine of x. But now the sine of theta is going to take the side that's opposite of the angle theta, take the length of that, divided by the hypotenuse. So that's going to equal to, the side opposite has the length of square root of 1 minus x squared over the hypotenuse. Well, again, the hypotenuse is 1. And dividing something by 1 doesn't change it. So here we can just write it as the square root of 1 minus x squared. So, in the end, the sine of the inverse cosine of x is equal to the square root of 1 minus x squared. And that makes us happy. So that's it. That's the end of this section. If anybody has any questions, comments, or problems, please make a note of it. Reach out to me during our next session, during office hours. And I hope everyone has a nice day.